Hello and welcome to Bio40 Pre-Lecture 30. Time to start messing with the Hardy-Weinberg assumptions. Last time, we talked about Hardy-Weinberg equilibrium. For populations with allele frequencies P and Q, where P is the frequency for the dominant allele and Q the recessive, the genotype frequencies will be P squared for homozygous dominant, 2pq for heterozygous, and Q squared for homozygous recessive. But this is only true if these 5 assumptions hold. The problem is, they never actually hold. You may be surprised to learn that many real-world populations do in fact have fewer than infinite individuals. We also talked before about how the mutation rate will never be 0. Additionally, mating usually isn't random, migration tends to occur unless geography prevents it, and selective pressures will always favor some genotypes over others. Minor violations of these assumptions are not a big problem. For instance, Hardy-Weinberg equilibrium is a good model for a very large population, even though it's still finite. But today, we're going to start talking about what happens with major violations of these assumptions. Such violations will change allele frequencies from generation to generation within a species. This is called microevolution. Macroevolution, or changes among species, is simply the accumulation of such smaller events over geologic time. We are going to focus on how violations of Hardy-Weinberg assumptions lead to microevolution. Over the next few lectures, we'll discuss the effects of small populations, non-random mating, mutations, migration, and selection. Today, our main focus will be on selection. The term fitness refers to an individual's relative ability to survive and transmit genes to the next generation. There are 2 components to fitness: viability and reproductive success. To contribute to the next generation's gene pool, an individual must both survive to adulthood and have offspring. From a gene pool standpoint, there is little difference between death and sterility. Fitness is assigned the symbol W, and it is always between 0 and 1. Suppose a homozygous recessive individual is only half as likely as a heterozygous or homozygous dominant individual to survive and have children. We would say that a heterozygous or homozygous dominant individual has a fitness of 1, and a homozygous recessive individual has a fitness of 0.5. Sometimes you'll also see the symbol S for selection coefficient. This is the inverse of fitness, the relative likelihood an individual won't survive and reproduce. Fitness is equal to 1 minus the selection coefficient. Natural selection describes the fact that individuals with higher fitness survive and reproduce more than individuals with lower fitness. So now let's talk about how we apply fitness to Hardy-Weinberg. At conception, the genotype frequencies are still p squared, 2pq, and q squared, as we've previously discussed. Then we need to define the relative fitness for each genotype. The genotype with the highest likelihood of surviving and reproducing is assigned a fitness of 1, and the others are given relative values as appropriate. The genotype frequency for the mating population will be the fitness multiplied by the zygote genotype frequency. For example, the homozygous recessive genotype frequency in the mating population is Q squared times its fitness. Let's imagine that the fitness for homozygous recessive individuals is 0. None of them survive and reproduce. Clearly, the recessive allele frequency will decrease, but by how much? Let's imagine the initial allele frequencies for gene R are p equals 0.9 and q equals 0.1. The genotype frequencies at conception are 0.81 for homozygous dominant, 0.18 for heterozygous, and 0.01 for homozygous recessive. We're saying no homozygous recessive individuals survive and reproduce, so their fitness is 0. There is no difference between being homozygous dominant or heterozygous here, so they both have a fitness of 1. Multiply the zygote genotype frequencies by the fitness, and you get the genotype frequencies of the mating population. 0.81 for homozygous dominant, 0.18 for heterozygous, and 0 for homozygous recessive. These are the numbers you use to get the allele frequencies for the next generation. And you do this just as before. The number of heterozygotes plus 2 times the number of homozygous dominant individuals, 0 here, is the number of recessive alleles. And divide by the total number of alleles, which is 2 times the total number of individuals, for Q equals 0.091. That's a 10% decrease from one generation to the next. In the same manner, we can see that P will be 0.909 in the next generation. It's okay that we're using frequencies here rather than actual population numbers, because those numbers would cancel out in division. Note that the specific decrease in Q will depend on what Q initially is. In our first scenario, where Q equaled 0.1, Q squared was 0.01, and 2pq was 0.18. Initially, the total number of recessive alleles is 2 times Q squared plus 2pq, but all the alleles in homozygous recessive individuals will be lost since they don't survive and reproduce. So the fraction of lost alleles is 2q squared divided by 2pq plus q squared, which is 0.1, the 10% decrease we just saw. When q is initially 0.5, 50% of recessive alleles are lost due to selection in a single generation. But when the initial q equals 0.01, only 1% of the alleles are lost. Interestingly, note that the decrease in q over a generation is equal to the initial q. So for a recessive lethal allele, the allele frequency decreases over time. But as q gets lower, the decrease in q from one generation to the next also gets smaller. The allele frequency appears to be approaching 0, but can it ever actually get there? Not by selection alone. Selection by itself cannot lead to the extinction of an allele. When q is small enough, the frequency of homozygous recessive individuals is low, and most of the copies of the recessive allele that exist are in heterozygotes who do not have reduced fitness. The recessive allele will persist in these individuals. In large populations, a balance is eventually reached where the number of alleles lost due to selection equals the number of alleles created by new mutations. So Q is stable. Since mutation rates are low, Q will be small in that situation. But there are some cases where the frequencies of recessive lethal alleles will be much higher. We call this heterozygote advantage. The classic example of heterozygote advantage is sickle cell anemia. This is a recessive lethal condition, but the allele frequency is as high as 20% in some areas. How can this be the case? In a typical scenario, we get the zygote genotype frequencies, assume the homozygous dominant and heterozygous fitnesses are equal, while the homozygous recessive fitness is 0, multiply to get the mating population genotype frequencies, and calculate the new allele frequency as we did before. This works out to 0.167 here. 20% of the recessive alleles are lost in a single generation. So what has to be different to maintain a Q of 0.2? Well, the homozygous recessive genotype is lethal. There are no recessive alleles being passed on from them. Recessive alleles will only be present in heterozygotes. So the only way Q can stay at 0.2 is if heterozygotes are 40% of the mating population. With the maximum fitness of 1, we get a frequency of 0.32 in the mating population. For this to be 40% of the mating population, the frequency for homozygous dominant individuals has to be 0.48. This works out if their relative fitness is 0.75. When heterozygotes have higher fitness than homozygous dominant individuals, the recessive allele persists at relatively high frequencies, even though the homozygous recessive genotype is lethal. In the case of the sickle cell anemia allele, heterozygotes have increased resistance to malaria compared to homozygous dominant individuals, thereby explaining the higher fitness. The recessive allele frequency tends to be higher in areas where malaria is more common. Anytime lethal alleles persist at high levels, some sort of heterozygote advantage must exist, or at least have existed recently in history. For instance, the allele that causes cystic fibrosis has a frequency as high as 5% in some populations. It's been hypothesized that this is the case because heterozygotes may be more resistant to diseases such as typhoid fever and/or cholera. That's all for selection. Next time, we look at what happens when other Hardy-Weinberg assumptions are violated. Okay, well, I did want to address another way to calculate how allele frequencies are influenced by selection. It's more complicated than what we discussed before, which is why I'm sticking this at the end as an optional approach. but it could make more sense to you if you're mathematically inclined. Like if you're bothered by the mating population genotype frequencies not adding to 1. This will also match more closely to what's in the textbook. We'll start much like before. With 2 alleles, we have homozygous dominant, heterozygous, and homozygous recessive genotypes. Respectively, the genotype frequencies of zygotes will be p squared, 2pq, and q squared. Each genotype will have a fitness associated with it, and the genotype frequencies at mating will be the zygote frequencies times the fitness. These frequencies should add to 1, but for that to work, they need to be normalized. Divide by the normalization factor W bar, which is equal to the sum of the mating population genotype frequencies. For our new allele frequency, we'll use the term Q prime to distinguish it from the initial allele frequency. It will still be the heterozygous frequency plus 2 times the homozygous recessive frequency divided by twice the total genotype frequency, which is the same as the normalization factor we just calculated. Alternatively, we just said that the total genotype frequency for our normalized values is 1, so we can just use the normalized heterozygous frequency plus 2 times the normalized homozygous recessive frequency divided by 2. Let's look again at our scenario where p equals 0.8 and q equals 0.2. Our zygote genotype frequencies are 0.64, 0.32, and 0.04 as we calculated before. We'll also use the same relative fitness values from last time. 0.75 for homozygous dominant, 1 for heterozygous, and 0 for homozygous recessive. Multiply the zygote genotype frequencies by the corresponding fitnesses to get the genotype frequencies of the mating population. 0.48, 0.32, and 0. Sum these frequencies to get a normalization factor of 0.8. Divide the mating population genotype frequencies by this to get the normalized values of 0.6, 0.4, and 0. Then, no matter which way you solve for q prime, you get 0.2. If it's difficult to follow this, but you like the earlier method we used, you can just use that. But if you prefer defined equations that you can plug numbers into, this is certainly an option. Real ending!